We are in our function unit, and for the first time, we get to use the word function. Up until now, we've been talking about relations, where relations are relationships between our two variables, x and y. A function is a special type of relation. A function is a relation in which each input has exactly one output. I'm highlighting that. I want you to highlight it in your brain. A function is a relation in which each input has exactly one output. It's really common to look at this picture of a function machine to understand what a function is. A function is a machine that takes a particular input, that's our x variable. It does something predictable inside our function machine, the same thing every time, such that given a particular input, a completely predictable output pops out of our function machine. So every time I input a given x, the same output y comes out. A broken function machine would, for the same input, sometimes have a particular y output and sometimes a different y output. That would not be a function. A function machine, a given input, exactly one predictable output. Before we look at some math examples of functions, let's look at some non-math examples. Our first non-math example is the function machine that, given an input of city, gives us an output of the state that city is in. Here is my what state is that city in function machine. Given an input of Seattle, my output into this what state is that city in function machine would be Washington. Given an input of San Diego, the output of my what state is this city in function machine is always California. Given an input of Bothell, my output is Washington. Olympia, my output is Washington. LA, as an input of the city, gives me an output of a state of California. Now, this is an example of a function. The input of Seattle has only one output, Washington. It's not in two different states. The input of San Diego has only one output, California. That's the only state it's in. Bothell, input, one output, Washington. Olympia, input, Washington is the only output. Similarly, LA. What's okay is that different inputs, Seattle, Bothell, Olympia, all have the same output of Washington. It's okay that the inputs of San Diego and LA both have the same output, California. What is necessary for a function is each input has exactly one output, which is the case for this function. Next example of a non-math function. And you're just going to have to not argue with me with this table, just take this one as reality. That every unicycle has one wheel. Every bicycle has two, just don't argue with me, it's just true. Every bicycle has two. Every motorcycle has two wheels. Every tricycle has three. Every car has four. And every minivan has four wheels. So taking this table, this representation of this relation as reality, this relation is a function, where my function is, given a vehicle, how many wheels does that vehicle have? So given any unicycle on the planet, if this table is true, we're going to assume this table is true, the output of how many wheels are on that vehicle is always one. If you tell me you have a tricycle, I can completely predictably predict that the number of wheels on that vehicle is 3. Similarly, input of car, always the same output, 4 wheels. Every minivan, output of 4 wheels. It's okay that cars and minivans both have 4 wheels. It's okay that bicycles and motorcycles both have 2 wheels. What's important is that each input has exactly one output. Every motorcycle, assuming this table is true, has exactly 2 wheels. Final example of a function. Here's my function machine. Your input is a word. My output of my function machine is how many letters are in that word. So it's a letter counting function machine. If you put the word dog into my function machine, inside my function machine is determining how many letters are in that word. Out comes the completely predictable answer, output of 3. Input of cat into the function machine. How many letters are in the word cat? Output of 3. Input of box. How many letters are in the word box? 3. Cup. 3. Input of frog. How many letters? Inside the function machine it counts. There are 4 letters. Star, input, output 4. This is a function. Given a particular input, a particular word, there are always the same number of letters in that word. It's okay that there are a lot of 3-letter words. It's okay that dog and cat and box and cup are all inputs with an output of 3. What's important is that the input of dog has exactly 1 output, 3. The input of cat, exactly 1 output, 3. Okay, those are examples of functions. For each input, there is exactly 1 output. Let's move on to some non-examples. So these 2 relations pictured below are not functions. Again, though, I need you to just take this table as reality. Every cranberry in the world is red. So there aren't any unripe cranberries, no rotten cranberries. All cranberries are red. Every strawberry is red. And last year my students said there's some other special hybrid white strawberry or something. No, those don't exist. All strawberries are red. And now apples, they're red too. Thus far, this is a function. Input of cranberry, color of that fruit, always red. Input of strawberry, output, always red. Input of apple, so far, color always red. But it's pretty hard to say that represents reality. There are a whole lot, I'm writing apple again, there are a whole lot of apples that aren't red. If you tell me you packed an apple in your lunch, that apple might be red, it also might be green, it also might be yellow. So given this table representation of the relation, relating fruit to color of the fruit, this is not a function. That's because if I input a fruit and the function machine is telling me what color that fruit is, just for this color of apple, this is where the problem is. This is the problem. The input of apple has 3 different outputs. Sometimes my apple is red, sometimes my apple is green, sometimes it's yellow. So this makes my fruit color function machine not a function machine. So it's not a function machine. It's a relationship between an input and an output, but not a function. Last non-example of a function. I always struggle with this one. 30 days, so we're looking at months and number of days. 30 days past September, April, June, and November. So 30 days in April, but all the rest have 31. March has 31. May has 31. And February has 28. As this is pictured right here, this is a function. It doesn't matter what year it is. I say, hey, it's January. And you're like, oh, cool, there's 31 days in this month. Oh, it's 1832 and it's April. How many days are in the month? Doesn't matter what year it is, there's always 30 days in April. Every year, 31 days in March. Every year, 31 days in May. So far, this is a function. But I hope that you are noticing why this is not a function. I'm missing an arrow. The arrow I'm missing is for the leap year. So sometimes February has 29 days. So if I say, hey, it's February, how many days are in this month? Sometimes you'll say 28. Sometimes you'll say 29. Therefore, this is not a function machine. It's a relationship between month and how many days are in that month, but it's not a function. Input of February, sometimes the output's 28, sometimes the output's 29. That is what makes this not a function. A way to say a relation is not a function is at least one of the inputs has more than one output. February, more than one output. Apple, more than one output of color. Whereas these other examples, these are all functions. Each input, exactly one output.